Uh, Today I'm going to give a presentation about the about the work FixMatch, simplifying semi-supervised learning with consistency and confidence. It is published in Europe's in NIPS 2020. So first, for the semi-supervised learning, sorry, I will first give some introductions about the semi-supervised learning. So one of the limits in applying the machine learning in practice is its reliance on the large label data. So as we know, collecting label data is expensive compared to the unlabeled ones. That requires manual effort in labeling each data samples. So semi-supervised learning addresses problems by allowing a model to be trained on a small set of labeled data examples with a large set of unlabeled examples. The goal of semi-supervised learning is to learn from the unlabeled data in a way that can improve the performance on the labeled data. So usually in the semi-supervised learning process, we will first training a model merely based on the labeled data examples. And then we will use these models to give the pseudo labels for the unlabeled data set. And then this model will update itself with the original label data and the data samples with the pseudo label. And then it will update iteratively until this model can achieve a good performance. So during the semi-supervised learning, one of the most important part is granting the pseudo labels for the unlabeled data set. So since if the model can grant more accurate labels to this unlabeled data, it can better train on the unlabeled data to achieve the finally better performance. Typical ways of this paper, the FixMatch, is the end of a series of papers in improving the semi-supervised learning method. So I will first review some semi-supervised learning method targeted to this FixMatch approach. The first is called the consistent regulation. Many semi-supervised learning methods rely on the consistent regularization to enforce that the model output remains unchanged, even when the input is changed. A common regularization techniques in supervised learning is data augmentations, which applies the input transformation to leave the class semantic unaffected. For example, in the image classification, it commonly to elastically deform or add some noise to an input image, which can dramatically change the pixels on the content of an image without changing its label. So for the consistent regulations it also applies the data augmentations to the semi-supervised learning by leveraging the idea that a classifier should output the same class distributions for an unlabeled data sample, even after it has been augmented. For example, originally we have unlabeled data, it is a horse. And then we will create some augmented image based on these data samples. And the model trained on the label data, or maybe on the last iterations, it will give some prediction result for the two augmented versions of this unlabeled data. And we hope that these two predictions can have the similar distributions and even have the same prediction vectors, so that enforce the model to have the more stable output patterns. So commonly in the semi-supervised learning method, they will use loss function similar like this. Here, this augmented X represented the different augmented data samples from the original unlabeled ones. And this P model represents the prediction vectors from the model. And we hope to minimize this loss to enforce that the to enforce that the examples should be unlabeled examples can be classified as same as as similar as among the augmented image samples. The second one is called the entropy minimization.
Jiadong, in the previous slides, which one is the unlabeled image?
This is the original unlabeled image, and these two are the augmented version of this original unlabeled data.
But if you just augment this unlabeled data, why it can help you to improve this training model? Because this one you still don't, even you like augment this image, you still do not have its label, right?
Yeah, they do not have the label. So the idea is we want the model to output the similar prediction result for the augmented version of the single data samples, which enforce the model to have a more stable output pattern.
So compared to which one?
To
be stable.
To be stable. Yeah, if we do not enforce, if we do not minimize this loss, then the models may give utterly different prediction result for the augmented version of even single original data sample.
So you mean, so for this two input, this two augmented input, you want to like get the similar output, right?
Yeah, we
But this augmented image is may change largely, like it has a large change. So if we just maintain the same output, I cannot figure out what does it mean. Because when you augment this image, now it's a host, probably it can become other things.
Yes, during the practice process, they will use some well-defined augmented algorithm so that they will not change the semantic. They will not change the semantic of the original data.
Of this image.
Okay. Yes, they will not randomly do the augmentation, but they need to preserve the semantic content.
Okay, I see. Okay, you can go ahead.
I have a question. So for the equation here, I mean, this is like a distance, right? We try to minimize the distance, right?
Yeah.
But the two terms, the first term and the second term is the same. I think the x is different, right? X is different.
In the paper, they say that this augmented can be some stochastic function, so that even for the same x, they will have a different output.
Oh, it's a stochastic function. Okay. Then the goal is trying to like help the model to learn like the common features of like the augmented images, right?
Based on my understanding, they want, since the semi-supervised learning need to learn from the unlabeled data, so they want the model to be stable, that it can exactly classify some unlabeled data to be unlabeled data, so that it can grant a confident label to this unlabeled data.
Okay.
So they want the model to be stable. It
Okay.
can even we use some augmented image from the original one, it can still recognize that they are the same things.
The same label, right?
Yes.
But the augmented image is generated artificially, or it's like it's data collected. It's not collected data, right? It's like some artificially generated data.
Yes, artificially generated based on specific augmentation algorithm.
And we don't have the label.
We don't have the label.
Then when you do we need to, because I'm not like very familiar with the semi-supervised learning. So do we need to create a label for the augmented image?
No.
The Y?
No.
No? Then the Y, what is the Y here? What is the value of the Y here?
Oh, the Y, there's a Y represented model itself based on in their paper. They are not the label.
Okay, the Y is the model. Okay.
Yeah.
But there is a model, right? The P, the subscript is the model, and the Y is also the model.
I think the Y is the model. During the paper, they do not give
from what I understand, it's like a more, the Y could be the label, but it might be a sequence of labels. And the P model here is trying to calculate the probability of each label, behind each label. Is that so?
No, this Y is not the label. Yeah,
the Y is not the label.
In their paper, they do not give a definition about this, what this is Y, but based on my understanding, this Y is not related to the label at all. Maybe it's just the model. Here
then if we don't have the label, then how can you make sure you make sure, because you have a prediction, you have a classification, right?
Yes.
Then the first term, when you compare the first term and the second term, you need to make sure that they are predicting to the same label, right? Otherwise, it doesn't make sense to use one to minus another one.
One minus another.
Because when you use the first term to minus the second term, and using the norm value, right? You want to minimize the distance when we predict the same or like the same augmented image. They will point into they will point to the same label. You want to minimize the probability that they belong to the different images belong to the same label.
Yes. If these two terms point to the different classification results, maybe they will mathematically have a large value. Only if they point to the similar, they point to the same classification result, and also they have the similar prediction distributions among different classes. This value can be minimized.
So the P model, the first term indicated the probability, right? It's like a scalar value or vector value.
It is the predicted class distribution.
Yeah, so it's a predicted class distribution. Then if it's a distribution, then the Y should be the label, right? If it's the probability distribution, it means the Y will indicate different labels, and the probability, the prediction will be the probability of different labels, right? So in machine learning, a classification problem is like, if we have 10 categories, then we will predict. So if we wanted to predict the X belong to which category, we just pick the category with the highest probability, right?
Yes,
but for each label, for each category, you can calculate a probability, right?
Right.
So I just wonder whether the Y is label, and it might be like indicate, it might indicate different labels, and the probability is the distribution, right?
Dr. Wang, maybe you mean is that the Y mentioned to different categories.
Right. The categories is actually the label, right? The label you are predicting.
Oh. I think the label is whether it belongs to each categories. Yeah. It can be the categories.
Yeah, the Y should be the categories.
Yeah. It can be the categories.
Right. And the P actually should be a vector. It's a vector of probabilities of different categories.
Yeah, of different categories. Oh, yeah. I have a misunderstanding about the category and the label. So I mean, whether it belongs to each category, I think is a label.
Yeah. So, okay, I got it. Yeah, that makes sense.
Yeah. So for the second approach in the semi-supervised learning is related to the entropy minimization. Yeah,
Can I ask you one more question? You go to previous slides. So here, if the Y is the label, so now if give this image, you don't know it's a horse, but in your model, your output label also does not have horse. In this case, how can you predict it to be the horse? it's like a model never see this image, this house.
Yeah.
In this case, how to input this Y?
This prediction result is from the model learned from some label data.
So that means it can still, even you do this step, it can still can only predict like the label that's the training of the training data. But for this unlabeled data, if they are not belong to this the label, if not belong to the training data, it cannot predict it.
Sorry.
That's like if like a training data has just use a digital, like training data only have 1 to 10. But now if this image is 11.
Yeah, he will
even you use this semi-supervised method, it still doesn't work. Because it never know the 11.
Even if in the label data we only have the category of 1 to 10, then the semi-supervised learning method is trying to classify image into 1 to 10. It will not recognize it into the 11.
But if that's meaningless for this method.
So we need at least one labeled examples in each category.
Yeah, I think probably it can only like increase the diversity of the existing data pattern. But for this unseen, unobserved data, it can like it still cannot predict.
Yeah, so for the semi-supervised learning, it's trying to help improve the performance that if we only have a very limited data samples on each category. But so under this scenario, the model is if we just train the model on the very limited label data, its performance will very inaccurate. So
that's why they don't like just like augment the training data, and then they can increase the training size.
Yeah, that's this is another perspective. Yeah, we can try to augment the label data and grant them the original data. Then we can create a larger label data set, right? Then we can train it on this on this larger label data set to.
Yeah, I think that's one. It's more reliable, right?
Yeah. Yes, but the augmented can only add some noise, but it will. Yeah, as you say, it cannot enlarge the diversity for the of the data samples. For example, for this table, it's like a horse on the grassland.
They can develop some method like to increase the diversity, just like to generate some sample. I think this should be much better than this method.
Yeah, that's the point. So, but maybe it is out of the semi-supervised learning scope. It's about how to create more powerful data augmentation algorithm.
Okay, I see. Okay, you can go ahead.
The second is about the entropy minimization in producing the pseudo label. So the pseudo label leverages the ideas of using the model itself to obtain an artificial label for the unlabeled data. A common underlying assumptions in many semi-supervised learning methods is that the classified decision boundary should not pass through the high density regions. Otherwise, the unlabeled data and its pseudo labels will increase a large amount of false labels. So based on this idea, the unlabeled data, in other words, should be granted with the prediction result have a high confidential. Here, the high confidential represents the low entropy. For example, we have an unlabeled data image, and the model will give some will give the prediction result for this unlabeled image. Maybe one example is that the prediction result is like this, such like this. Then the second prediction result is like this, and the statistics like is this. And then we will use the argmax functions to transfer this prediction result to a one-hot classification vectors. For example, here the 0.4 is the largest one, then it will belong to the class false. So the false value is 1, others are 0, and similar like this. And then we will calculate the difference between the original prediction result and its transferred one-hot prediction vectors. And if these vectors have the low entropy, we think that it will equals that the prediction result have a high confidential values. And then here the here for the theta is the threshold that we enforce that only if the largest prediction values larger than the threshold, we will think it is a good predictions, and we will use these predictions to grant the pseudo label. Otherwise, if the largest prediction result among different classes are all less than the threshold, we will think it is incorrect predictions. So we will not use this use this result to grant the pseudo labels. And here is the theta threshold. And if this, for example, if these two prediction results are all fulfill this threshold, and then we will calculate the entropy for this prediction result. And we hope that the models can grant the low entropy can produce the low entropy prediction result for the unlabeled data, so that the model have a high confidence in recognizing this unlabeled data into different categories. So that is called the entropy minimization. This entropy minimization.
But if for all the unlabeled images, so the prediction are very bad, so that means he cannot give the pseudo label. He cannot increase his training set, right?
Yeah, right.
Okay.
But during the training process, if we add these loss functions in the training process, we will enforce the model to give the prediction vectors with the lower and lower entropy. So finally, we will have some good predictions to the unlabeled data. So here, this entropy minimization combined with this consistent regulation are the two methods applied in the semi-supervised learning in recent years to help improve the performance of the semi-supervised learning. Then a series of semi-supervised learning papers published on the top conference from the first one, the mix match, and the second, the remix match, and finally to the paper I present, the FixMatch, a series of semi-supervised learning methods based on these two mechanisms to improve the performance step by step. So instead of introducing the FixMatch at the front, I will first introduce the mix match, which is the original version of the FixMatch proposed method. So as a typical method in many semi-supervised learning methods, they use the data augmentation on unlabeled data. So during the mix match, for each data samples in the unlabeled data sets, they will generate k different versions of the augmented data. And then the mix match will produce a get label for the examples using the average of the model's predict class distribution across all the k augmentation results. So using the data augmentation to obtain an artificial label for the unlabeled data example is common in the consistent regularization method. Since for the consistent regularization, we want the classify output the similar prediction distributions for examples, even it have been augmented. So here we directly using the average values among different argumentation versions can directly make this can directly make the guess label similar to all its argumentation versions. So that is their idea. Using the average among different argumentation versions to fulfill the consistent regularization. And another point is called the sharpening. It is match the entropy minimization. Since we have a prediction result, which represents SP, we will use these functions to help sharpen the prediction result, which makes the value that make the prediction result with the highest values to be more higher, to dominate the distributions among different categories. This function is called the temperature sharpening method. For example, if here the control parameters is called the T, the temperature, as the T equals to 0, or equals to not equals to 0, but approach 0. The output of these sharpening formulas will approach nearly a one-hot distributions. That the values with the prediction result among different categories with the largest value will near to 1, and others with lower computation scores will near the 0. So it will help sharpening the prediction result, which fulfill the entropy minimization. So that is this label guessing with different argumentations and the sharpening in the prediction result are the two main ideas in the mixed match semi-supervised learning method. So based on this method, another groups improving this mixed match called the remix match. So their motivation is that the primary goal of the semi-supervised learning algorithm is to incorporate with the unlabeled data in a way to improve the model's performance. One way to formalize this intuition is to maximize the mutual information between the model's input and the output for the unlabeled data. Intuitively, a good model prediction should depend as much as possible on the input. So such assumptions can be mathematically equals to maximize this formula. To interpret this result, we can first observe that the second term in this formula is very familiar. It's just the entropy minimization objective, which we want to minimize the average of the prediction entropy. Then we can minimize the entropy of each predictions to help minimize these terms. That is what the semi-supervised learning usually to do. But however, for the first term, it had not been used in the semi-supervised learning techniques. So what is this term? It is the entropy of the average prediction result. So this term encourages that on average across the entire training data set, the model predicts each class with equal frequency, which makes this model to be fair. For example, if we only have 2 prediction results, we want them to be maybe one is the 1, 0, and another is 0, 1. So for the average of this prediction result, it should be 0.5 and 0.5. So this average prediction result will have the lower entropy. And in other words, the prediction models is very fair. It is fair to grant different classes with equal frequency. However, there's a problem that this objective cannot be directly applied into the semi-supervised learning method because if the model, because if the training data, if the category distributions in the original data set is uneven, so we cannot directly enforce the model to have the equal frequency in different categories. So in this paper, they use the method called the distribution alignment to do the to lowering the entropy of the average prediction result. Result that over the course of training, we will first maintain a running average of the model prediction on unlabeled data. So given the model prediction result P on unlabeled data, we will scale Q by the ratio of this one. And this ratio can be explained as using the label distribution of the labeled data to divide the average of the model predictions for all unlabeled data. So they will use this ratio to help normalize and scale the prediction result for each unlabeled data to enforce that the model, to enforce the prediction result for the unlabeled data can be aligned with the labeled data. That is called the distribution alignment. And the second improvement for the remix match is called the argumentation arcane. Yeah, so as the Dr. Yuan had mentioned that maybe the argumentation method can produce some image that's dramatically different to the original one. So if we use the model to give the prediction results for this to these augmented versions, maybe they cannot help to increase the performance, but lowering the performance since they are very different to the original one. So during the remix match method, they will first generated a weak augmentation version of the original one, which they only add some noise to the original data to preserve most of the semantic content, and then they will use the prediction result for these weak augmentation versions directly for this for other strong augmentation version. That, for example, these 5 papers are the strong augmented version, and their prediction result can be different. But however, we will not use this for prediction distributions. We will directly use the prediction for this weak augmented version as the prediction result for this 5 augmented image. So that this is called the augmentation arcane, and this is the arc. So these 2 points, the distribution alignment and the augmented arcane, are the two improvements in the remix match to help improving the semi-supervised learning method. But however, also although this improving the detailed techniques on each stage of the semi-supervised learning method can improve the performance, the model will finally become more and more complex and incurs a longer training time. So in this paper, the FixMatch, they break the trend for the recent state-of-the-art method that increasingly complex mechanism and produce a method that's more simple, but still can achieve an accurate performance. Here, the FixMatch is a combination of 2 approaches, the consistent regulations and the entropy minimization, like this. It will first generated 2 versions of the original unlabeled example. First is called the weakly augmented. Another one is the strongly augmented. And then the models trained on the labeled data will give different prediction values on these 2 versions. And however, they will just use the weakly augmented. They will use the prediction result for the weakly augmented versions as a pseudo label. Here they still use the argmax functions to create the pseudo labels for this augmented image. But however, they will still try to minimize the entropy between the pseudo label for the weak augmented version and the prediction result of the strongly augmented version. So that in this paper, they simplify the entropy minimization and data augmentation into one loss function. That first they created two augmentation version, and also minimize the cross entropy between these two augmented versions. So that is a very simple idea in this paper. For the unlabeled data, they will use these functions to minimize the cross entropy. And for the labeled data, they just use a cross entropy loss, simple cross entropy loss to entropy loss to training the data set, to training the model. So that is the whole technical parts for the FixMatch. So that is why they called simplifying semi-supervised learning method. So any questions on the techniques about this FixMatch? If there are no questions, I will come to the experiment result. Since their methods are very simpler than the mixed match and remixed match version, but during the experiment, the author claimed that they have a better performance. In particular, they use the SAM network architecture, the SAM training protocols, including the optimizer, learning rate schedules, and other hyperparameters during the experiment, while comparing with the different method. Here note that only the remix match, mixed match, and the UDA are the leading semi-supervised learning method in recent years. And the mean teacher, pseudo labeling, and the second model are very old version of the semi-supervised learning method, which have a very bad performance. And in this paper, I have introduced the mixed match and a remix match. But for the UDA, it's another stories. Maybe I will send the emails about these papers after this presentation. So based on this result, here it is not the accuracy. The value is the error rate. So a lower error rate means a larger accuracy. In this during this based on this comparison result, we can see that on these three data sets, CIFAR 10, CIFAR 100, and SVHN, their fixed match algorithm can achieve better performance. Compared to the leading other semi-supervised learning method. And here the RA and the CTA are the different augmentation algorithm used in the fixed match. However, there is only one exception in this result is that you can see that for the CIFAR 100, the remix match can have a better performance compared to the fixed match. The others do. The others also recognize these situations, and they do the many experiments typically on the remix match and fixed match on the CIFAR 10, and finally find that is the distribution alignment makes the remix match better than their fixed match method. And the others apply the distribution alignment in the fixed match approach, and then they found that if the fixed match can use the distribution alignment, it will perform better than the remix match. So based on this result, the authors are very confident in claiming that their FixMatch is simpler and better than other semi-supervised learning method. And also for the ablation study, they have the author have do many ablation studies on the in the experiment, but it all relate to the different hyperparameters. I think these results trivial in the presentation to discuss. So I only show one examples about the threshold for this the threshold for the threshold theta. We can say that the threshold of the we can say that the threshold value of 0.95 maybe the 95% shows the lowest error rate, though increasing it into the 97% or 90%, it did not hurt the error rate much. In contrast, the accuracy drops by more than 100 points percentage when using a small threshold values. So it means that when we're doing the semi-supervised learning, a larger threshold are very important in improving the performance. However, note that the threshold value controls the trade-off between the quality of the models and the quantity of the pseudo labels granted in each iterations. So here the impurity represents the error rate of the unlabeled data that falls above the threshold, where the mask rate represents the number of examples that are masked out. So we can see that the accuracy of the pseudo labels for unlabeled data increase with the higher threshold values, while the amount of the unlabeled data contributing to the training process is decreased. Let's say that only 92% of unlabeled data can be utilized in training the semi-supervised learning model, but it will have a very lower error rate. This suggests that, however, we can see that the error rate decreased to 5.5%, while the max rate decreased in 8%. This suggests that the quality of the pseudo labels is more important than the quantity of reaching a high accuracy. So that it also demonstrates the observation in this figure that the high computational threshold is more important in training the model. So that's all of this paper. So yeah, just for the NIPS paper, they are very simple, just giving an idea and doing some experimental evaluations. So any questions about this paper?
So what do you think, which is the most exciting part of this paper?
To be honest, I do not have some most exciting part in this paper. But
do you like this paper? Do you like this paper?
Yes, I like this paper. Okay. Because yeah, because they just use one loss functions to combine the entropy minimization and the data augmentation. It is very graceful compared to the previous version of the semi-supervised learning method. One loss functions can achieve better performance. I think it's very
It's simple, but it works, right?
Yeah, it works. And it also demonstrates that instead of adding more and more detailed techniques in each stage, maybe we can just use some simple but graceful method to solve the problems. And also, why I want to present this paper is that from the mixed match to the fixed match, we can see the process that different groups try to improve the semi-supervised learning method just from the two motivations, but they can do different improvements in different stages. And a series of paper, yeah, I think it's a good story.
Okay, so any other question?
So any attacking methods for such supervised learning? If we do the like a data poisoning, how can we defend such attack?
Sorry, during this paper, they do not mention.
Right,
that.
I know. Yeah, the question is out of the scope. I know.
Yeah. I don't. Yeah, last time the last paper I presented is a poisoning attack to the semi-supervised learning method.
I see. Okay. Yeah, I guess it's a little bit like forget about it.
Yeah.
Okay. I will try to record the video.
So maybe I can first.
It's fine. I can find the video from our seminar website.